Okay, welcome to the next chapter on variational methods for computer vision, and this next chapter is on diffusion filtering. So it basically expands on what we talked about in the last chapter. In the last chapter we talked about filtering and how to do filtering. We talked about smoothing filters, and we talked about derivative filters, and today we will treat a more sophisticated and more elegant approach to filtering, which leads us almost directly to so-called variational methods. And this is the diffusion filters. Many of you will have some intuition about what diffusion is. It's a physical phenomenon that we have in our everyday lives, and what I will show you today is that you can use that phenomenon to process images and to filter images in a very smart way. Diffusion filters, at least in the general sense, are nonlinear filters. So in contrast to the standard Gaussian filter, there are linear diffusions, of course, but the whole power of diffusion filtering comes in when you do nonlinear diffusion filtering. And the diffusion filters, they can be implemented by so-called partial differential equations. So I'll talk a little bit about partial differential equations. Then I will introduce diffusion, and then I will introduce also nonlinear and so-called anisotropic diffusion processes. And I will mention a little bit about the numerical implementation of these filters. Nonlinear filtering. To motivate why nonlinear filtering would be interesting, let's start with what we've already seen, the Gaussian filter. So that's a simple convolution with a Gaussian kernel, and as you may remember, it basically means it's a weighted sum of the colors in the vicinity, where the further away they are, the less they get weighted. The smaller their weight, so the central pixel is most weighted, and then the weights decay exponentially as defined by this Gaussian kernel. This is a classical example of a linear filter. It can be implemented very efficiently. Convolutions are generally very efficient to implement, because what you can do is you can go to the Fourier space. We are not going to really talk about that in detail, but in the Fourier space, the convolution is nothing but a product. So if you do a Fourier transform of G and a Fourier transform of F, and then just take the product of values for every pixel, and then back transform to the inputs for the original X space, then you get the same as the convolution. That in itself doesn't really make it faster. What makes it faster is that there are fast Fourier transforms that can be implemented efficiently, and in fact the fast Fourier transform goes all the way back to Gauss himself, who suggested that. In practice, however, linear filters are often suboptimal. They remove noise, and this is good, but they also remove the signal. So they create a substantial blurring. We already saw that in the last chapter in the comparison between the Gauss filter and the median filter. Gauss filter being a linear filter, the median being a particular nonlinear filter. The difficulty with the median filter is it works quite well, and it's used very frequently, but it's very hard to generalize that to other types of nonlinear filters. And so while the median as a recipe is a good thing to have and to know, it doesn't generalize easily. And so today with the diffusion filters, we'll talk about nonlinear filters that generalize more easily and that have a very intuitive interpretation. So what we would want to do is an adaptive denoising, a denoising that somehow preserves semantically important structures. And as I said, the key challenge is, of course, we don't know which structures are semantically important. But for example, we might argue if there is a strong brightness edge, there is an indication that this is semantically important, and then we would like a Gaussian blurring that blurs a little less in that location compared to other locations. And in principle, you can do that. So a somewhat naive way, you see this Gaussian kernel has some width sigma. What we can do is we can try to adapt that sigma for every pixel independently. And so we have a different sigma at every pixel. So the idea would be to have some convolution or something like a convolution where sigma depends on the image here. So at every x we have a slightly different sigma. That would be a solution to the problem, a direct kind of modification of the Gaussian blurring to make it adaptive. And that in fact has been tried, has been done, but it turns out there is a far more elegant solution to the whole problem. And this is the diffusion filtering. The key observation underlying diffusion filtering is that this Gaussian blurring that we see can be interpreted as a diffusion process. A diffusion process in the sense that you consider the gray value you see at every pixel much like a concentration of some substance. And that substance diffuses over time, and that creates this averaging or blurring. So it's much like if you put salt into a soup. In the beginning you have salt in one location, and with time things diffuse. Or some other kind of pepper or whatever substance you want to put in the soup. And this process is called the diffusion process, and it's actually very related to the Gaussian smoothing. In fact, we will see that for the simplest diffusion process, the solution of that process is nothing but the Gaussian smoothing. But the good thing is that the diffusion generalizes very elegantly to nonlinear diffusions and adaptive diffusions. But before we go into diffusion, since this is, since there's, some people have more math background, some less. So what I wanted to start with is a little of a quick review of differential equations and partial differential equations, because the diffusion is a particular differential equation. But before I go into diffusion, I wanted to recap a little bit what differential equations are and why they are important. I believe they are very important. In fact, the study of physics is mostly a study of differential equations. And pretty much everything in our world can be modeled by differential equations. All the phenomena that you see in your everyday life, we can model them mathematically, and the framework is differential equations. To give you some examples of differential equations, this is a differential equation. So a partial differential equation is simply an equation for a function and its various partial derivatives. So any equation containing derivatives of a function is called a differential equation. And more specifically, partial differential equation means the function has multiple variables and there are derivatives to several of these. For example, this is called a wave equation. It basically says the derivative of that function psi, the second derivative in time, is proportional to the second derivative in space. That's an equation. Where it comes from, we'll skip for today, but typically all of these equations can be derived from very simple basic principles. And if you've had physics and remember some of them, the pendulum, for example, it's very easy to derive a differential equation that models a pendulum. And then you get these kinds of differential equations. Similarly, you can derive the wave equation. This equation is a so-called ordinary differential equation. This is a particular subclass of partial differential equations, namely if I only have one single variable. And the pendulum, for example, has one variable. X is basically the location of the pendulum at time t. Or a spring, if you want, how much you extend the spring, and the extension of the spring at time t is x of t. And then m would be the mass attached to that spring, and k would be a coefficient that depends on the material of the spring. There are soft springs and harder springs, and so that is the coefficient k here. And you probably know the K if you've ever had a friend who tuned his car and changed the springs. I had one when I was studying, and it's not good because every time we hit a bump, you know, it would hit you in the back because the springs were so hard. He somehow liked that. It's more a race car type feeling, but it really hurts your back. And so what he did is he changed the K in the springs, essentially. This is a material dependent quantity. And then you have that term in the middle that also has a physical interpretation. For example, if you put your pendulum in honey, then you get a friction. And that is the friction term. It's proportional to the velocity of the pendulum. So the faster it moves, the larger the friction. And so you have all of these physical parameters that represent your system, and that is then the equation. And the good thing is you can just study that system, study these parameters, set up that equation, and once you solve it, you can predict how the pendulum will move. And how do you do that? Well, you find a solution to that differential equation. And so much of physics is about modeling the world with a differential equation and then solving it. Finding a function x that fulfills that equation. How do you do that? Well, it turns out a lot of physics revolves around differential equations that have analytical solutions. And it often seems that if there is no analytical solution, the physicist doesn't like it. He will try to avoid problems that cannot be solved analytically. And so a lot of the study revolves around equations that can be solved analytically. For example, here's the wave equation, and you can try for yourself if you plug in sine of x minus ct. So that's a sinusoid that just moves with a constant velocity. If you plug that in this equation, you will find it fulfills the equation. It's not difficult to see. If you take the second derivative in time, you get c squared times the sine. If you take the second derivative in space, you get just the expression itself again. And so, in fact, this is a correct solution. It's not unique. Typically, there are multiple solutions. In physics, there have to be multiple solutions because the initial condition isn't specified. And depending on the initial condition, of course, the system will move differently. But once you fix the initial condition, typically it specifies the behavior. And this is what I said here. So you can get unique solutions in general by imposing boundary or initial conditions to these problems. For example, fixing what the shape of that wave front is at time 0. Similarly, here we have the pendulum. I dropped the friction for now, so this is called the harmonic oscillator in physics. So the mass and the spring coefficient k, and the solution there, as you know, is just a sinusoid, for example, or cosine if you want. And again, if you plug that in here, you find out that the frequency by which it oscillates, this omega, is square root of k over m. And so indeed, I remember that in the car where k was larger, the oscillations would be faster. The frequency is faster. And it's funny because you can actually predict all of these things without actually measuring things. And so there is quite some power in these differential equations. If you have an analytical solution such as this one, it allows you to predict what would happen to the same system if I change this or that term. What would happen if I increased the mass? And indeed, if you put a lot of weight in your car and then you go through a hole, then it will oscillate more slowly than if you have less weight. And you can just read it off in the solution. So these analytical solutions are very powerful to understand the world we live in and to predict what happens to our world if we change things. So these are examples of analytically solvable problems. Unfortunately, most differential equations are not solvable analytically. And so, for example, many of the equations we have in image analysis, we have to solve them numerically. That is not as beautiful. It doesn't allow you to do the same kinds of predictions as an analytical solution does, but it gives you some way to study the world. Numerical solution basically means, in practice for a time-dependent process such as this one or that one, it means you fix some initial condition that is usually given, and then you compute how does the thing change once I move a little bit, and this basically tells me how does it change over time, and then you accumulate the changes numerically in a computer and determine what would be the system configuration at time epsilon, at time 2 epsilon, 3 epsilon, and you stepwise move into the future. This is one simple way of numerically discretizing. We'll see a little bit how that works in a second. Diffusion is a particular phenomenon in physics that can also be represented by a differential equation, and since we want to study it a little more, here I decided to give you the physical derivation of the diffusion process. The diffusion process comes through actually two aspects. The first aspect is called Fick's law. It says that if you have a concentration of some material, substance, say in a liquid, and the concentration is not constant, then this varying concentration in space creates a flow of substance, right? So if you have more, say, salt or pepper in one location than in the neighbor location, the salt will diffuse. And how fast will it diffuse? The speed of diffusion, this J is the velocity by which it diffuses, depends on how strong is the concentration gradient, how strong is the variation of concentration. If the concentration is constant, the gradient is 0, there is no diffusion. But if there is a gradient in the concentration, a change in space of the concentration we call U, then the velocity is proportional to that gradient, and the proportionality factor is called G often, and it's called the diffusivity. And that is typically material dependent. So you know, for example, in some substances the material diffuses faster and sometimes slower. And there are materials where the diffusion is orientation dependent, so-called anisotropic materials, where diffusion goes fast in one direction but very slow in another direction. That can happen. The second equation is a so-called continuity equation, and that is also something that's quite intuitive. Once you have a flow of substance, that changes the concentration. If the salt flows away from a certain location, then the gradient of then the concentration at that location will decrease, right? If the salt flows away, it decreases. How does it decrease? Well, the divergence tells me how much is the flow changing in space. This is again the gradient operator. So the nabla operator applied to the flow J is a vector, so it's the divergence. And so the change in time of the concentration is equal to the negative divergence. Why is that? Well, if you just have a flow, that doesn't mean the concentration changes. If a substance flows through a material, the concentration at a given location doesn't change. It only changes if the incoming flow is different from the outgoing flow, right? If the same amount of substance comes in and comes out, it doesn't matter how fast it flows. What matters is what is the change in flow there. And that change in flow is the divergence, is how does the flow speed change at that location. And that tells me how the concentration changes in a time step, in a time instant. And now you have these two equations. This is called the continuity equation. It basically says that the substance cannot disappear. That's all it says. So if it moves away from a location, then the concentration decreases and it moves to some other place, but it cannot just disappear in total. And so these two equations basically are the backbone of diffusion, and you get the diffusion process just by plugging the J in here, right? If we plug that in here, the two minus signs cancel out, and what we get is the change of concentration. U over time is given by the divergence of G times the gradient of U. So we simply remove this J, the flow, by plugging this equation in here, and we get a single equation for U, for the concentration at a given location at time t. And this is called the diffusion equation. I'll stop here and we'll continue next time. Thank you.